Hello everyone, welcome back to our course on abstract algebra. Today we're going to introduce a new algebraic structure called the integers modulo n, denoted by z modulo nz. And this is one of those objects that we are going to create by abstract algebra. So we are going to start from the integers, and out of the integers we're going to construct something new that behaves sort of like the integers. So it's sort of like a toy model of the integers, but we'll also see that they also behave quite differently from the integers in very interesting ways. So just as a reminder, last time we talked about the integers and their addition and multiplication and the axioms that define the integers. The integers are closed in their addition and multiplication. Addition and multiplication have some properties. There is a 0 and a 1. There are additive inverses. And especially to define the integers, we define the natural numbers, which is a subset that satisfies these properties. What we're going to do is use the integers to construct something new that also satisfy 1 through 3, but we'll see that they have other properties that are also interesting. Those are what we call the integers modulo n, and in a sense, it's something you have already seen before because we use the integers modulo n when we keep track of time. So let me show you how, what is it that we do. So for example, suppose that it is 2 p.m. and let's say that 27 hours go by. What time is it? Well, to keep track of time, what we do is we look at the clock and we start counting. So the first, when we go 10 hours, we reach here, and then we don't go into the, say, the 13th hour. We reset the time, and it's sort of the 0th hour, and then we keep going from there. So when I do 24 hours, when I do 12 hours, now it's 2 a.m., and then I do another 12 hours on the clock, and I get back to 2 p.m., and then I have 24 plus 3, and I have another 3 hours that they're gonna bring me to 5 p.m. So the answer is that the time will be 5 p.m. tomorrow. So what happened? How did we actually do this? First of all, 2 p.m. is sort of like military time, or in a 24-hour clock is the 14th hour of the day. And so 14 hours have passed on today. And then we're going to look at 14 plus 27 and then see what time that is. That is 27 plus 4, that's 31, and 10, 41. And then what we can do is subtract multiples of 24 because those are entire days, and we know that the clock resets after an entire day. So this is 24 plus 17, and 17 is in fact 24 is 17 is 12, so that brings us to noon, plus 5. So this tells me that, so we can sort of like discard this whole multiple of 24 because an entire day goes by. This tells me that is now afternoon, and this is telling me that it's going to be then 5 p.m. So what we did is, if you want, you can just, we could have stopped, if you are okay with military time, say, we could have stopped at 17, that's 5 p.m. So we treat the number of hours in a way that we can disregard multiples of 24. We do division by 24 and then look at the remainder, and that will tell me what the time is. So for example, here's another one. So it's 2 p.m., 2 p.m., and let's say 327 hours go by. Then what is the time now? All right. Well, I know that 327 hours is, in fact, 24 times 13. So that's 24 hours. So 13 days plus 15. What I did here is do long division of 327 by 24 and get a remainder of 15. So if we started with 14, the 14th hour, and add 327, what's going to happen is that I have 14 plus 24 times 13 plus 15. So I do have multiples of 24 in here, and then 14 and 15, that is going to give me 29. But that gives me one more multiple of 24, so that is 24 times 14 plus 20 plus 5. So then it turns out that now the time, again, I can disregard the entire days, the time is just 5, which indicates in the 24-hour clock that it is 5 a.m. So after 327 hours, we will reach 5 a.m. What's happened here is that we are just counting hours, disregarding multiples of 24. So that is exactly how what's happening here is that we are working in what we call Z modulo 24Z, where every number only counts, I only care about numbers, but I only care about the remainder of dividing that number by 24, which is exactly what happened here, that I, instead of 327 hours, I divided by 24. I don't care how many days have gone by. What I care is it's the remainder after I divide by 24. And that is Z modulo 24Z is going to be the possible remainders modulo 24, which is 0, 1, 2, up to 23, and all of them just considered up to what we call modulo 24, that if I am at the 23rd hour and I add 1 hour, then I'm at the 24th hour, which is the 0th hour, so it goes back to 0. So let me do this in a more formal way. So we are going to define what we call congruences. So let A and B be integers and n bigger than 1. We say that A is congruent to B modulo n if n divides B minus A. That notation is divides, and that means n divides B minus A is the same as, so I'm going to write it down, n divides the quantity B minus A, or n is a divisor of B minus A, or B minus A is a multiple of n, or more formally, that B minus A is n times k for some other integer k. Okay, so for example, 7 is congruent to 2 modulo 5 because 5 does divide 7 minus 2, which is 5. But 13 is not congruent to 6 modulo 5, because 5 does not divide 13 minus 6, which is 7. Okay. And with this congruence class in mind, now what happens is that the integers, so for example, if I look at, let's take n to be 5, and I'm going to look at the congruence classes modulo 5. So what numbers are congruent to 0? 0 is congruent to 5 and congruent to 10 and congruent to 15 modulo 5, because their differences are multiples of 5. Also, 0 is congruent to minus 5 and it's congruent to minus 10 and it's congruent to minus 15 modulo 5. So what we call the class of 0 is going to be all the numbers a, integers, such that a are congruent to 0 modulo 5. These are precisely the multiples of 5, which is sometimes just written 5 times z. What are the numbers that are congruent to 1? Well, it would be numbers that are, a number minus 1 is a multiple of 5. So if I add 5 to it, I get numbers that are congruent to 1. So 1 is congruent to 6, and 11, and 16, etc. Those are all congruent modulo 5. And also, if I subtract 5, that's also a number that is congruent to it. So 1 is also congruent to minus 4, and minus 9, and minus 14, etc. Modulo 5. So here now, the class of 1 is going to be those integers a, such that a are congruent to 1 modulo 5. And those are, in fact, all the numbers of the form 5k plus 1 for k some integer. Okay, and then what happens is that, well, if you draw a number line, I have 0, 1, 2, 3, 4, 5, 6, 7, minus 1, minus 2, etc. Then 0 and 1, 2, 3, 4, 5. So 0 and 5 and minus 1, minus 2, minus 2, minus 1, minus 5. Those are in that class. And then 1 is congruent to 6 and also to minus 4. And 2 will be congruent to 7, but also to minus 3, etc. And then you see what happens is that there is this sort of like a cyclic behavior that the numbers, the classes just repeat like this. So there's only finitely many classes of numbers modulo 5, and every integer is in one of these classes. So every integer is in one of these classes. It's either congruent to 0, or is congruent to 1, or is congruent to 2, congruent to 3, or congruent to 4, and that is it. Every integer is congruent to one of those. And in fact, I can show you that that is true, because if I have any integer, say n, then I can do long division by 5. Remember the theorem that was the division algorithm. I can write 5q plus r, with q and r integers, and r between 0 and 5. Okay, but that this is an r, it looks almost like a 5. Then what this is telling me, notice that then since r and n differ by a multiple of 5, we do have that n minus r is 5q, and therefore r is actually congruent to n modulo 5. Remember that the congruence, two numbers were congruent if their difference, n minus r, is a multiple of 5. So R and N are congruent modulo 5, and I can pick R. R is going to be some number between 0 and 4. So the upshot of this is that N is congruent to R modulo 5 for some R, which is the remainder by division by 5, between 0 and 4. So it is in one of these classes that we had above. And that is what happens for every N. So in general, for any N bigger than 1, Z can be broken up into the class of 0 and the class of 1 and the class of N minus 1. And those completely partition the integers like that. We also call this is the class of 0 modulo N. That's the class of 1 modulo N. And that's the class of N minus 1 modulo N. And every integer is in one of those. And if you want to know what is the in what congruence class they are, you can do long division by N, and the remainder will be the class where they land. Great. So this is going to be what we call Z modulo NZ. Is going to be exactly, it's going to be the set of congruence classes. Sometimes we write that Z modulo NZ will be the class of 0, the class of 1, and the class up to the class of N minus 1. So notice that there are N elements, and each one of the classes is a subset of the integers, or more simply, we write that is 0, 1, up to N minus 1, knowing that those are considered as numbers modulo N. And the interesting part is that I can do addition and multiplication on Z modulo NZ. So I'm going to endow Z modulo NZ with an addition and a multiplication, where the addition is going to be defined as follows. If I have a class of A and the class of B, that is going to be the class of A plus B. In the congruence notation, what you say is that, well, the class of A modulo N plus the class of B modulo N, how I'm going to add them up? I'm going to add A and B, and then I'm going to reduce it modulo N. So for example, when N was 5, I can do, for instance, the class of 3. Let me write it first with the brackets. The class of 3 plus the class of 4 is going to be the class of 7. But the class of 7, if I reduce modulo 5, 7 minus 5 is 2, is exactly the class of 2. So the class of 3 and the class of 4 gives me the class of 2. Similarly, if I do 3 modulo 5 plus 4 modulo 5, then what I get is the class of 7 modulo 5, which is 7 is congruent to 2 modulo 5, so I get the same answer. Then the class of 3 plus the class of 4 gives me the class of 2. So that is my addition on Z modulo NZ, and then I can also endow it with a multiplication, which is going to be the class of A times the class of B is going to be the class of A times B. In congruence condition notation, we have the class of A modulo N times the class of B modulo N. That is A times B modulo N. And for example, that tells me that, let's do again the same example we had before. So if N is 5, the class of 3 times the class of 4 will be the class of 12. And the class of 12, 12 is 2 plus 10, which is a multiple of 5. So this is the same as the class of 2. So in the mod n notation, 3 modulo 5 times 4 modulo 5, that will be 12 modulo 5, and 12 modulo 5 is the same as 2 modulo 5. So I get that 3 times 4 is 2 in this new operation. Now, you have to prove that this is actually well-defined. Are these operations well-defined on Z modulo NZ? So what that means is that I'm picking representatives for the class of A and for the class of B, but I could have picked a different representative. So if the class of A is the same as the class of A prime, and the class of B is the same as the class of B prime, because those are just representative numbers. So for example, as like numbers like 2 and 7 are numbers that represent the same class modulo 5. What I want to know is that if I add those, if I add A and B, that should give me the same answer as if I add these two. And if I multiply those classes, that should give me the same answer if I multiply those classes. Okay, let me show you. Let's do the addition and prove that that this is actually true. So suppose that the class of A is the same as the class of A prime, and the class of B is the same as the class of B prime. And I want to end up showing that the sum is actually the same. So this implies that A and A prime are congruent modulo n, and this implies that B prime is congruent to B modulo n if they are in the same class. And that implies then that A minus A prime has to be a multiple of n. I'm going to call it, say, n times r. And B minus B prime has to be a multiple of n. I'm going to call it s for some r and s integers. And now let's see what happens if I add A and B. So A and B, I want it to be exactly modulo n, I want it to be the same as A prime plus B prime. So what I'm going to do is, first of all, substitute A for formula for A prime. So from here, I actually have that A prime, or A, is A prime, or A prime is A minus n times r. And B is B prime minus n times s. So this is the same as A prime plus B prime plus a multiple of n, which is actually minus r minus s. But notice that the integers are closed under addition. The integers are closed under inverses, so they have additive inverses. So these are integers, and then I add two integers, I get an integer. Okay, and therefore these is congruent to A prime plus B prime modulo n. So this tells me that the class of A plus B is actually the same as the class of A prime plus B prime, and therefore that's what I want to show, that addition is well defined. Okay, so we have addition, and similarly multiplication is well defined on classes, and you can, if you want, as an exercise, show that multiplication is well defined on congruence classes. And it turns out that, well, Z modulo NZ, so I've picked an n bigger than 1, fixed, and it turns out that Z modulo NZ under addition and multiplication satisfy the following properties. The integers modulo n, so the set 0, 1, 2, up to n minus 1 considered as classes modulo n, have the following properties. One, z modulo nz is closed under addition and multiplication. If I add two congruence classes modulo n, I get a congruence class modulo n. If I multiply two, I get a congruence class modulo n. Two, addition and multiplication are commutative, associative, and distributive, just like the properties of addition and multiplication of the integers. Let me show you that is the case, that addition and multiplication are commutative. So let A and B be like two classes modulo n, and what I want is, I want A plus B is congruent to B plus A modulo n. So let me show you what happens if I do, well, how much is B plus A minus A plus B? I'm hoping that that is a multiple of n. But when I do this, what do I get? Everything cancels out and I get 0. And 0 is a multiple of n, is 0 times n. So that tells me that A plus B is congruent to B plus A modulo n, and therefore addition is commutative in this new algebraic structure. Similarly, you can prove, and again, I leave that as an exercise, that this addition multiplication is associative and distributive. Those are quite simple. And three, first, there is a 0 element, which is going to be the neutral element with respect to addition. And that is precisely the number 0. The class of 0 modulo n has the property that A plus 0 is just A, is congruent to A, and is congruent to 0 plus A modulo n. It does not change the congruence class if I add 0. And there is also a 1 modulo n, the class of n, the class of 1 modulo n, such that A times 1, well, it is A, and it is 1 times A modulo n. And finally, for all the classes, if I have a class modulo n, then there is a class that we're going to call minus A modulo n. What is that class? Such that A plus minus A is the same as minus A plus A modulo n, which is congruent to 0 modulo n. What is that class? In here, minus A is the class of minus A, or the class of minus A modulo n, which is actually also the class of n minus A modulo n, if you want to put it as a number between 0 and n minus 1. So we can show that, for example, I can show that, so if I take any integer A, okay, so and n bigger than 1, what happens if I add A and n minus A? Well, if I add A and n minus A, that is going to be just n, which is a multiple of n, and that tells me then that A plus n minus A is congruent to 0 modulo n, and the same way n minus A plus A is congruent to 0 modulo n. So the class of n minus A works like the additive inverse of the class of A in this addition. Okay, so let me go back to this slide and then recap that the integers under addition and multiplication, they satisfy properties 1 through 3, just like the integers themselves. So that is one thing, one new algebraic structure that satisfies 1, 2, 3. And more importantly, is that, well, it does not even satisfy number 4. There is no set that works like the natural numbers, because otherwise these would be the integers also, but these are not the integers. And there are two key properties of z modulo nz. Number one is that z modulo nz is finite. it has n elements. So unlike the integers, which are infinite, z modulo nz is finite, and finiteness is wonderful, because if you're trying to do operations with the integers in a computer, soon enough we run out of memory when the integers become larger and larger and larger. However, since z modulo nz is finite, every operation stays within this finite set of numbers. And for example, this, even in the most simple of all cases of z modulo nz, z modulo 2, which is a set with exactly 2 elements under congruent classes modulo 2, has found incredible applications in computer science, and engineering, because, well, just the whole binary systems, the bits in computers, those are following these arithmetic. It's this set z modulo 2 under addition and multiplication that have found incredible applications in computers. So that is a great thing. This is sort of like a toy model of the integers, but only with finite number of elements. Remember that we had other examples of algebraic structures that satisfy 1, 2, and 3. For example, the rationals under addition and multiplication, the reals under addition and multiplication, the complex numbers under addition and multiplication. But these are all infinite. So this is the first example that we've seen of something that satisfies those properties 1 through 3, where the set itself is finite. Now, another key property, and this is more of a warning, is that even though they satisfy 1 through 3, and they look and feel very much like the integers, the integers modulo n also have some properties that are very different. They can be very different from the integers. So for example, take n equals 6. Then what happens if I multiply 2 times 3? The class of 2 times 3 is the class of 6, but 6 is 0 modulo 6, so this is the class of 0. So this is non-zero. 3 is non-zero, but they multiplied to something that is 0. And that is a very different behavior. This does not happen in the integers. In the integers, we always have that if a times b is 0, then a is 0 or b is 0. We also have that in the rational numbers, in the reals, in the complex numbers, but not in z modulo nz. And this has catastrophic consequences because, for example, in z, we also have that if a is non-zero and a times b equals a times c, then we can deduce that b equals z. The cancellation laws, and they rely on this fact, but we're not going to be able to do that in the integers modulo n. This property, this does not work in z modulo nz in general. So we will have to be careful about that. What we're going to say is we're going to invent some new terms, and we're going to say that these, because these are factors of 0, these are called zero divisors. And when you study more algebra and things like rings, then you study the rings, the zero divisors in a ring and the units in a ring, so that you know when are you going to be able to do cancellation and when not, when you are not going to be able to do that. Okay. Let me finish by doing one more construction of z modulo nz from a more formal point of view. So now another point of view. of Z modulo NZ is the following. We start with the integers, and then we're going to define a relation on the integers. If you've learned set theory, then you know what a relation is. We're going to say that a relation which we're going to denote by congruence or congruence modulo n. We're going to say that two integers are congruent, they're related, if A is congruent to B modulo n. Okay, so if n divides B minus A. Then we're going to show, and I'm going to leave this as an exercise, you can show that this relation is symmetric. That means that if A is congruent to B, then B is also congruent to A. And you can see that clearly that this implies that n divides B minus A, which in turn implies that n divides A minus B, and in turn that implies that B is congruent to A. Okay, so it's symmetric, it's reflexive. A is always congruent to A, and that is again because n divides n minus A all the time, which is 0. So A is always congruent to A, and it is transitive, meaning that if A is congruent to B and B is congruent to C, then A is congruent to C. And I'll leave that for you to prove that that is true. And what this says is that then Z under this relation, because this is reflexive, symmetric, and transitive, that says that this relation is an equivalence relation. And therefore, equivalence relations partition our sets into equivalence classes. So Z modulo, or Z up to this relation, this is the set of equivalence classes. So here is going to be the class of 0, the class of 1, etc., where the class of 0 are all the integers that are related. Oh, that's a terrible name for a letter here. Let's say integers k that are related to 0, and so on. And it turns out that you can prove, like before, that these equivalence classes are precisely the classes of 0, 1, up to n minus 1, and that is also what we call Z modulo NZ. So you can consider Z modulo NZ as the set of equivalence classes of Z under a equivalence relation. And then we can give an addition and multiplication to those equivalence classes like I just did before. So this is another way of constructing Z modulo NZ using the theory of equivalence relations. Okay, so I'll stop here for now, and in the next video, we'll start with groups. So we'll start with group theory in earnest.